So we also need to be able to explain how to convert Denary numbers to their binary representation equivalent. So let's take a look at a couple of examples. So we want to represent -103. So we do the same thing as we've been doing for all of the binary numbers we've been working on so far, and write down the values of our placeholders. Now right away we can see that this is a negative number, so hopefully you've understood that the most significant bit has to be a 1. And then we apply the logic we've learned to represent binary numbers for the rest of it. So we're working with 103, so we have to put a 1 at the 64, which is going to leave us with 39 left to represent. So we put a 1 at the 32, which will leave us with 7. So no 16, no 8 is too much. We have to take a 4, which leaves us with 3. We have to take a 2 to leave us with 1, and the 1 leaves us with a remainder of 0. So this would be the signed bit equivalent value of -103. People forget that we can still represent positive numbers, so let's just look at positive 103. So 1, 2, 4, 8, 16, 32, 64, 128. So we need to remember there's a positive in this 103, so a 0 goes at the front, and we apply the exact same logic as we used previously to count them up. And you will see that the only difference between the positive and negative numbers is that the most significant bit is a 0 rather than a 1 to make it positive or negative. Now, it's very straightforward to do signed bits, but remember there's 2 representations of 0, which is not great, and when we look at the arithmetic later on, the arithmetic functions are very difficult, and often the results of the calculations don't work out. So those are the 2 reasons that signed bit is not really used anymore.